Namaste. Welcome to the next video of Machine Learning Practice course. In this video, we'll start discussing how to implement linear regression models with sklearn. We start our discussion by building what is called as a baseline regression model. As you know, any baseline model helps us to generate a reasonable baseline based on some kind of a common sense prediction. sklearn implements a dummy regressor class that helps us in creating baseline for regression. Let's look at a sample code snippet. The dummy regressor class is implemented by sklearn.dummy module. We instantiate a dummy regressor object by specifying the strategy for making the prediction. Here we have specified the strategy as mean. That means we'll be making predictions based on the mean value of the label. So we learn this mean value of the label by through the fit function on the training set. So we look at all the training labels and learn what is the mean value of the prediction. We'll use this mean value later to predict for the test samples. And we calculate the score due to this particular prediction by using the test data. The score returns R square or coefficient of determination. We'll study R square or coefficient of determination later in this module. So dummy regressor makes a prediction as specified by the strategy. And the strategy is based on some statistical property of the training set or a user specified value. There are 4 strategies that are supported by dummy regressor. First is the mean, second is the median, third is the quantile, and fourth is the constant. Which quantile to be used as a prediction is specified by a quantile parameter, and the constant value is also specified by the user through the constant parameter to the dummy regressor constructor. Now that we have created a dummy regressor baseline, let's start to do something more intelligent with the training data that we have, and we'll start actually building some linear regression models based on what we have studied in the theory course. Let's understand how to train a linear regression model in sklearn. In first step, we instantiate object of a suitable linear regression estimator from one of the following 2 options. So we know that the linear regression can be solved with one of the 2 methods. One is normal equation and second is iterative optimization. So let's first understand how to solve linear regression with normal equation. So we first instantiate the object of a linear regression class, and this linear regression class is implemented in sklearn.linear_model. So this is how we instantiate the linear regression object. The other option is to use iterative optimization. The iterative optimization is implemented by SGDRegressor. It is again implemented as part of sklearn.linear_model module. So we can either use linear regression for normal equation or SGDRegressor for iterative optimization. Second, we call fit method on linear regression object with training feature matrix and label vector as arguments. So here we use a linear regressor object which could be either from linear regression or SGDRegressor, and we call a fit method with 2 arguments. One is x_train, which is a feature matrix, and y_train is a label vector. And both the feature matrix and label vector come from the training set. And this particular way of constructing a linear regression model works both for single and multi-output regression. In multi-output regression, the second argument in the fit, which is y_train, will be a label matrix instead of a label vector as in the single output case. And why would it be a label matrix? Because we have multiple outputs in the label. Let's study SGDRegressor in a bit more detail because it provides a lot more flexibility than the linear regression class, which is used to solve the normal equation method. So SGDRegressor Estimator implements stochastic gradient descent algorithm. It is used for large training setup with more than 10,000 samples. And SGDRegressor provides greater control on optimization process through provision for different hyperparameter settings. Let's look at different hyperparameters that we can specify in the SGDRegressor. So we can configure SGDRegressor for different loss functions. There are two loss functions that we can use. One is squared error, which is a standard loss function that we have also studied in the context of linear regression in the theory class. And second is a Huber loss, which we have not studied in the theory course. Huber loss is used for making the linear regression robust to the outliers. So if you suspect that you have outliers in your data, you can use Huber loss for training the SGDRegressor. We can also specify different penalties in form of regularization. So if you want to perform regularization inside SGDRegressor, we can set the penalty parameters. There are three penalty parameters that are supported. One is L1 regularization, L2 regularization, and elastic net. Elastic net is a convex combination of L1 and L2 regularization. Then we can also specify the learning rate. So learning rate can be specified to a constant learning rate, optimal learning rate, inverse scaling, and adaptive learning rate. By default, SGDRegressor uses inverse scaling as a learning rate as a way of deciding learning rate for each iteration. But we can also specify the other three learning rates as well. And finally, we can also provide the way to stop the SGDRegressor iterations. We have a parameter called early stopping that we can set to true or false. Early stopping helps us to stop the iterations of SGDRegressor once we reach a specified condition of convergence. So there is a small tip that it's a good idea to use a random seed of your choice while instantiating SGDRegressor object. It helps us in getting reproducible results. So we can set the random seed with a parameter random underscore state in the constructor of the SGDRegressor. Here I have set the random seed to 42, but you can set it to any value of your choice. In the rest of the presentation, we won't be setting the random seed for sake of brevity. However, while coding, it is recommended that you always set the random seed in the constructor of the SGDRegressor object. So let's try to understand how to perform feature scaling for SGDRegressor. Remember that SGD is sensitive to feature scaling. Hence, it is highly recommended to scale the input feature matrix. We can perform feature scaling through pipeline construct. We can use feature scaling. We can use one of the methods that we studied in data preprocessing for feature scaling. Here we have used standard scalar as a method for feature scaling. So we have standard scalar followed by SGDRegressor. So what will happen is that in this pipeline, the input matrix is first scaled according to standard scalar method, and then SGDRegressor is applied on the input on the transformed feature matrix. So feature scaling is not needed for word frequencies or indicator features. These features have intrinsic scales and they do not need any feature scaling. Features extracted using principal component analysis should be scaled by some constant C. That helps us to make sure that the average L2 norm for, the PCA transform feature matrix is equal to 1. And that way the transform data through PCA can be used inside SGD. Let's try to understand how to shuffle training data after each epoch in SGDRegressor. We can simply set the shuffle parameter in the SGDRegressor constructor to true. That way, the data will be shuffled before every epoch in the SGDRegressor. Let's try to understand how to set learning rates in SGDRegressor. So we can set learning rate to constant, inverse scaling, or adaptive. So here the default setting for the learning rate is inverse scaling. We use eta 0 as 0.01 and the power underscore t hyperparameter as 0.25. So there are these two parameters eta 0 and power underscore t, which are two important parameters that helps us to decide the learning rate. SGDRegressor uses different learning rate in different iteration, and that learning rate in inverse scaling is decided by the following formula. So the eta, that is learning rate for the iteration, is calculated as eta 0, which is the initial learning rate, divided by power of t, which is the current iteration. So we raise current iteration to power underscore t. So power underscore t is another hyperparameter that we set for deciding the learning rate in every step while using inverse scaling learning rate. So we can make changes to these parameters, that is eta 0 and power underscore t, to speed up or slow down the learning process. And how do you know whether to speed up or slow down? We can look at the learning curves. We can look at the value of the loss function after every iteration. If loss is changing too slowly, we need to speed up the training process. And if there is some kind of oscillation in the loss, that means the learning rate is too high, and we need ways to reduce it. And we can control the speeding up or slowing down of the learning rate through eta 0 and power underscore t parameters. So let's see how to set a constant learning rate. So we can simply call SGDRegressor constructor with learning rate set to constant, and this constant learning rate is specified in eta 0. So we have specified 0.01 as a learning rate, and that will be kept constant throughout the training process of SGDRegressor. So let's try to understand how to set adaptive learning rate. So we have to specify learning rate style to adaptive in the constructor of SGDRegressor, and we have to specify what is the initial learning rate through eta 0 parameter. So in adaptive learning rate, the learning rate is kept to initial value as long as the training loss decreases. And when the stopping criteria is reached, that is training loss does not decrease further, the learning rate is divided by 5 and the training loop continues. Okay, so we keep the learning rate constant till we reach the stopping criteria, and at stopping criteria we change the learning rate, and the way we change it is by dividing it by 5 to the existing learning rate, and then we continue with the training loop again. Now we need a stopping criteria, and we stop the algorithm when learning rate goes below 10⁻⁻⁶. Now that we have set up the learning rate, we also need to understand how to set number of epochs in SGDRegressor. In this case, there is a parameter called max_iter that we can set to the desired number of epochs, and the default value for max_iter is 1000. So we can set max_iter parameter in the constructor of SGDRegressor. And here I would like to remind you that one epoch is one full pass over the training set. So it has been found through experimentation that SGD converges after observing approximately 10⁶ training samples. Thus, a reasonable first guess for the number of iterations for n sample training set is we can actually divide 10⁶ by n, which is number of samples in the training set, and we take the ceiling value of this particular division and set max iter to that particular value. If we do that, then possibly our SGD regressor will converge. We can also stop SGD regressor by specifying stopping criteria. Let's study how to use different stopping criteria in SGD regressor. So option 1 is to set a stopping criteria based on three parameters. One is tolerance, second is n_iter_no_change, and max_iter. So here the SGD regressor stops when the training loss does not improve further. For n_iter_no_change consecutive epoch, so if training loss does not improve for a specified number of consecutive epochs, the training stops. And if this condition is not met, we stop the training after reaching the maximum number of iterations that is specified in max_iter. So through these three parameters, we can specify the stopping criteria for SGD regressor as one of the options. In the second option, we specify the early stopping criteria. The early stopping criteria, we need to specify two more additional parameters, which is early stopping equal to true, and we also have to specify the validation fraction. The validation fraction is used to set aside some data as a validation data. And we use the score method to obtain the validation score. Now the SGD regressor stops when validation score does not improve by at least the tolerance value for specified number of consecutive epochs, and that threshold is specified by n_iter_no_change parameter. Else the SGD regressor stops after reaching the maximum number of iterations specified in max_iter parameter. Let's study how to use different loss functions in SGD regressor. So we can set the loss parameter to one of the supported values, which is squared error, which we have studied already in the course, or we can use other losses such as Uber loss, and you can actually find out more about these losses in the sklearn API documentation. But the loss value, the point here is the loss value has to be specified in the constructor of the SGDRegressor object. So here earlier we have seen that there is a squared loss and Uber loss. Those are two losses that we can use here. So what happens is SGD provides weight update after looking at every sample. So when SGD does that by looking at one sample, when it provides the update by looking at one sample, the SGD updates might be a bit unstable. So we can give a better weights by updating the weight vectors based on average of some previous updates. And averaged SGD specifically does that. So we can do averaging across all updates as one of the options by setting average equal to true. So we have to set this average parameter in SGDRegressor constructor and set it to true. When we do that, we get the weight, next weight updated to average of weights from the previous updates. In the second option, we set average to some integer value. When we set average to integer value, averaging begins once the total number of samples seen reaches the average. So what we do is we ignore first few samples and we start averaging only after we exceed the specified number of samples in the average. So for example, setting average equal to 10 would start averaging after seeing 10 samples. So this is how we can specify the integer value in the average argument. So average SGD works best with a large number of features and higher value of eta 0. And eta 0, to remind you, is the initial learning rate that we specify in the SGDRegressor. So sometimes what we do is we do multiple runs of SGDRegressor and we want to actually use the value of the weight vector at the end of the previous SGD run as the initialization for the next SGD run. We can do that by setting warm_start parameter to true. So here, while instantiating the SGDRegressor object, we set warm_start to true. So by default, this value is false. That means every time we run SGDRegressor, it is initialized to a new weight vector, and whatever work we have done in the previous run of the SGDRegressor is ignored. So let's make use of warm_start parameter to monitor SGD loss iteration after iteration. So here what we do is we set max_iter equal to 1. So we are going to make one iteration of SGDRegressor with warm_start equal to true. We use a constant learning rate with the learning rate specified in eta 0. Now what we do is we basically run this loop for 1000 times, and in every iteration we call SGDRegressor fit object on training set. Now what will happen is when we are calling the fit, we are actually using the value of the weight vector from the previous iteration because we have set warm_start equal to true. Then we get the prediction and calculate the mean squared error for that iteration. So this is how we can keep track of SGD loss iteration after iteration. Now that we have seen how to train linear regression models using sklearn APIs, let's move on to the next topic, which is how to inspect the trained model. So the specific question that we are asking here is how to access the weights of trained linear regression model. Remember that the linear regression model obtains the label as a linear combination of features. Specifically, y is equal to w0 plus w1x1 plus w2x2 all the way up to wmxm, where m is total number of features that are used to describe a given training example. And we can compactly represent this as w transpose x, where x is the feature vector for this particular example. So here, as part of the training process, we learn the weight vector, that is these weights, which is w0, w1, w2 all the way up to wm. So the weights w1 to wm are stored in coif_class variable of linear regression object. So we can access that by simply calling linear regressor object dot the coif_, this is the member variable where w1 to wm weights are stored. The intercept weight, which is w0, is stored intercept_class variable. So we can access that by calling the intercept_class variable on the linear regressor object. Note that these code snippets work for both linear regression as well as SGDRegressor. And for that matter, this works also for all regression estimators. Why does that work? Simply because all of them are estimators, and we have seen that sklearn API is kind of designed in such a way that all estimators share some kind of common methods and member variables, so that it makes it easy for us to remember those methods and member variables and use them in our code without really worrying about what kind of estimator object is being initialized. So let's understand how to make inference in sklearn. So specific question that we are asking is how to make predictions on new data in linear regression model. So there are two steps. We first arrange data for prediction in a feature matrix of shape number of samples by number of features, or in a sparse matrix format. In step 2, we call the predict method on linear regression object with feature matrix as an argument. For example, here we have linear regressor object and we call predict method on it with x underscore test, which is a feature matrix for the test set, as an argument. And this will return the predicted label for the test set. And again, the same code works for all regression estimators. So in this video, we studied how to train linear regression model with normal equation and iterative optimization. We use linear regression class for solving linear regression problem with normal equation method, and we use SGDRegressor class for solving linear regression problems with iterative optimization method. We studied SGDRegressor class in detail and looked at various parameters that it provides for us to tune the optimization process. Later, we looked at how to inspect the model by accessing the weight vector through coefficient and intercept member variable of the linear regression object. Finally, we looked at how to make predictions on the new data. So this gives you a set of tools for solving linear regression problem. In the next video, we will study how to evaluate linear regression model trained through one of these estimators. Until then, goodbye and namaste.